Hello guys, welcome to second law of thermodynamics, where I'll be explaining the heat engine, which is everything for the second law of thermodynamics. Now before that, I'd like to summarize the statement for the second law, which states that, well, energy spreads out over time. So this explains the limitations to the first law of thermodynamics. So, well, when two materials or two molecules interact with each other, well, tiny bits of energy in terms of friction, viscosity, etc., well, they affect the interaction, right? And essentially there are no perpetual motion, so that means perpetual machines cannot be made. Because, well, let's say we have this physics equipment right here. As you know, if the ball swings here, it transfers its momentum to the last ball such that this goes here and again swings back. So here this keeps on swinging like this, and eventually it stops because, well, when the two balls collide with each other, there are some tiny bits of energy lost as friction and even sound energy, and eventually that builds up over time, stopping this whole motion. Now to the heat engine, there are two types. First one is the SS type, source sink. So here the source of, let's say, a heat energy at temperature T1 gives heat Q1 to the working part. So it does some work like this. But here, according to the second law, it must lose some heat, let's say Q2, to the sink because of, well, spreading out of the energy due to friction and that. So here the efficient work done is Q1 minus Q2. So our efficiency formula is output by input into 100%. So our output here is the work done by Q1 into 100%, which is Q1 minus Q2 by Q1 into 100%. So therefore our efficiency is 1 minus Q1 Q2 by Q1 into 100%. Now since Q2 is never 0, that means we have 1 minus something into 100%, and, well, this is always less than 1. If Q2 is never 0, that means that efficiency can never be 100%. And here the statement for this type is called the Kelvin-Planck statement, which states that without losing heat to the sink, a heat engine cannot be operated. So now for the second type, it is based on the working mechanism of a refrigerator. So our refrigerators or fridges keeps our food cool. That means it continuously applies a cool heat flow from, well, the cold body to the hot body, which, well, is not possible unless there is some external energy. And in the refrigerator case, we put the plug into the socket, so the electrical energy helps to do the continuous heat flow from cold body to hot body. So the second type, cold to hot body, or the fridge one. So here we have a cold body, and let's just say it applies Q2 to the working part, because first you need some working part to convert to essentially give off the same heat energy to, well, the hot body, right? Ooh, I'll make this straighter. Let's say this is heat Q2 and Q1, and this is some work done on the body, right? So that means our efficiency is again output by input into 100%. Now our output is actually Q2 because we're trying to transfer the heat energy to the hot body, right? To keep our foods warm, we want to do that. So we have Q2, and then, well, the input is essentially the work done. So this into 100%. And now since the work done is never 0, that means, well, the efficiency is never 100% because this is always less than 1. Now this is also called the coefficient of performance, also known as COP, and we have the second statement, also known as the Clausius statement for heat engine, or for the second law of thermodynamics in terms of heat engine, which states that without doing continuous work to the system, heat cannot flow from the cold body to the hot body, or essentially the heat engine cannot be operated. So in the next video, I'll be doing the Carnot engine, the cycle of the Carnot engine, also known as the Carnot cycle. And if you learned something new, please like and subscribe. Thank you.